Okay. Inverse, and I didn't spell that right. Inverse matrices to solve linear systems. I want to show you the idea behind today. Math is always based on some other math, and it's so true. That's why it's so important every time I give you guys a lesson that you learn it, or even the previous year, because everything in math is really based on something you did previously. It's like on top of itself, blocks or something. Foundation of a home. If I had 3x equals 12, and I needed to solve that, algebraically, most of us would say you divide both sides by 3, and you get x equals 4. Now, any mathematician will tell you that the proper, language is that we are multiplying here, and we have to be able to undo multiplication. And the way you undo multiplication is with its inverse. In fact, especially you Miss Chappie people, it's the multiplicative inverse. And so that's where you would divide by, multiply by 1/3. Is the same thing as dividing by 3. And you would do it to both sides, multiplying both sides by 1/3, which is the same thing as dividing by 3. Those would cancel, and you would get x equals 12 over 3, which is really 4. Same answer. This is kind of the backdrop of what we're going to do today. There's a certain thing called an inverse. 1/3 is the inverse of 3. There's an inverse that deals with matrices, and that's what we're going to get into, because it's kind of like division, how those cancel each other out, and that's the idea for today. So, a couple of ideas. Whenever you see this with a letter, capital letter, that's usually talking about the determinant. Whenever you see capital letter -1, you're talking about an inverse. Alright? Just wanted to throw that out there. Don't worry about that example yet, because I want you to get this key concept right here. This key concept, the inverse. How to find the inverse of a 2x2 matrix is given like so. Alright? The basic idea is you got to find the determinant. That's what this is. The inverse equals 1 over the determinant times the matrix here, but it's changed. Look what's changed here. The A and the D has flipped, and the C and the B have changed signs. So in other words, the diagonals flip from top left to bottom right, and the bottom left, top right diagonal, they just change signs. So they don't move, they just change signs, and that means they don't always become negative. They change signs from whatever they are to the opposite sign. And this here again is the determinant, and you multiply that times each one of those. It's like a scalar, and you multiply that times each one of those. Let me demonstrate that to you over here with this example here. Find the inverse of A. Okay, the first thing you need to do is find the determinant. So I'm going to write it like that. That's the determinant. Okay, that's what I have up here. That's the determinant. So the determinant of A diagonally is going to be 15 minus 16, which equals -1. Alright, 15 minus 16, which equals -1. So the way this works is the inverse of A is going to equal 1 over the determinant, forgot what I was saying, times, now listen, you don't just take A. It's really important. You flip the 5 and the 3, and the diagonal here, 2 and the 8, stay where they are, but they change signs. That's what you have to do. Alright? So again, notice what happened, that the diagonals here, that the diagonals here flipped. The 5 and the 3 flipped, no sign change. These diagonals here, the 2 and the 8, they just changed sign. So that's basically -1 times 5, -8, -2, 3. And when you do your math here, you'll get -5, you'll get 8, you'll get 2, and you'll get -3. And that is your answer. Alright. Now I took the time, kind of skipped ahead. I took the answer from my inverse. And look what I did here. I took my inverse and I multiplied it by, oops, that's not the determinant, so let me get rid of that. I multiplied it by A here. A is the original problem up here. So I took my inverse times A, and the order matters here, so I put my inverse in front. Alright, so the inverse times the original. Let's look at what we get. I went ahead and did the multiplication, so hopefully you remember that, how I got these numbers here. But when you add them together, I get 1, 0, 0, and 1. Now what the heck? You remember from the last set of notes? That's basically like 1. Remember, that's the identity matrix. That's how you, if you multiply this times any 2 by 2 matrix, you'll get that same 2 by 2. Now why would I get the matrix version of 1? Well, that goes back to this. What happens when you divide 3 by 3? You actually get 1x. What happens when you multiply 1/3 times 3? You actually get 1x. We just don't write the 1. So it makes sense. If you take your inverse, which is this, and you multiply it by your original, which is this, you should get 1. And again, this is a matrix version of 1. So this, finding the inverse, is a way that we're going to use to solve some equations, actually. Alright, so I have this matrix equation here. AX equals B. And we need to solve this for the matrix. I just forgot to write matrix X. So X, our answer, is going to be a matrix. So here's A, here's B. Now, the basic idea is if you're going to solve this equation, you just simply divide by A or multiply by the inverse of A, but you have to do it to both sides. And the order in which you do this, since we're talking about matrices, is important. Those cancel out and you'll get X equals 1 over A times B, which is the same thing as B over A. Here's the short version of how we're going to solve this. We're going to take and find the inverse of this. And we're going to multiply by this. But we already know that that's going to equal 1. You can do 2 multiplying, but I'm not going to do that. We already know that this is going to equal 1. The main thing is to take that inverse and multiply by this. Okay, so that's what we're going to do. That's the main important step. So the determinant of A is going to be 8 minus 7, which equals 1. It's not always going to be 1 and -1, okay? But the determinant of A is actually 8 minus 7 when you multiply those two, and so you get 1. So now the inverse of A, remember the symbolisms, is really 1 over 1. That 1 is already in the formula. And again, I'm using that key concept earlier. 1 over 1 times A, we switched around. So it's 4 and 2. Those two switch. And this 7 is positive and this 1 is positive. Why? Because you got to flip the 2 diagonal ones for A, and the other diagonal ones just change signs. Okay, so this is just going to be 1 times all this, and you're just going to get 4, 7, 1, 2. Alright, so that's the inverse. That's the inverse of A. Now we should take this and multiply by both sides. And so real quick, I'm going to show you that. Okay, I wrote it out already for the sake of time. Now, I took this inverse times that equation there. Now, again, it's like this step right here. What happens is those cancel out. So I automatically know that that should go to 0 if you did everything, go to 1, excuse me. The identity matrix. So I'm not going to do that. If we were to sit here and do the multiplication, we should get the identity matrix. We will get this. But I know it already does. So that's canceled out. And notice that it goes in the front of each matrix. That's important. The order matters. The inverse when I say it. The answer here is going to come from these two matrices being multiplied together. That's the answer. Alright, not having a pencil, I messed up. But I went ahead and multiplied these. I keep skipping because, for the sake of time, and we should already know how to multiply. I multiplied these two matrices, and when you do, you'll get negative 84 plus 4, 12 plus negative 14, negative 21 plus 24, and 3 plus 4. And so my final answer, my X matrix, is 0, negative 2, 3, and negative 1. That's my answer there. So basically, you just have to multiply your inverse matrix in front of the equal sign matrix. Alright, I want y'all to get this down. Go ahead and pause that, and we'll finish here in a second. Okay, what you just saw is the key concept of how to actually solve a system doing what we just did. We just solved the equation, but now we're trying to solve a system. So the first thing you need to do is make up your coefficient matrix, which we're going to call A. So my coefficient matrix is 2, 1, negative 3, 4. We've made those before, just the coefficients of that. And then we're going to multiply that by our matrix of variables. We call that X. So it's simply just X and Y. Many times if it's just a 2 by 1, that's called a vector. And then our matrix of constants, which we'll call B. So it's just in the same form of the AX times B thing. And we get 19 over negative 7. And so they just really want us to write basically the same thing using matrices, no plus signs and equal signs other than, right here or whatever. And real quick, if we were to just say 2 times X plus negative 3 times Y, that would equal 19. It's the same equation if we did the matrix multiplication. 1 times X plus 4 times Y. You'll still get the same thing. It's actually just the same thing rewritten. And so the basic premise is we first need to find the inverse of A, and we're going to multiply that by B. That's what we're going to do, and do it in front. So I'm going to do this for the sake of time. Find the determinant and the inverse. And you go ahead too. Okay. So what I did was found my determinant, and then I found the inverse. But I didn't go ahead and multiply it. You can multiply this and get 4 over 11 and 3 over 11 and negative 11 and 22. Negative 1 over 11 and 2 over 11. I said that wrong. That's negative 1 over 11 and 2 over 11. But that's hard to multiply. What I think makes more sense is to do that last and to go ahead and multiply your two matrices first. Do this one times that in that order, this one first, and then go ahead and then do the 1 over 11 scalar. Okay, so I went ahead and multiplied those two. 76 plus negative 21. I know you can't see it, that's why I rewrote it over here. That's 55. Negative 19 plus negative 14. Again, that's this times this, and plus this times this, and this times this, plus this times this, and you get these. And then I wait to do my scalar, which is simply 5 over negative 3. I shouldn't put that fraction bar there, and I did it over here too. It shouldn't be there. But the idea is simple, that x, y vector, which is really x, equals 5 over negative 3. So what is the solution? It's not this. It is 5 comma negative 3, because we know that they intersect at a point. So here is another way for you to figure out how to solve a system of linear equations. And so this is the last one, and you probably hear a lot of noise in the back. All right.